Have you ever noticed a very strange phenomenon? When you drive those top-tier EVs on the market that boast 0-100 km/h in 3 or 4 seconds through city streets, that instant pushback acceleration feels like the internal combustion engine can already be thrown into a museum as a historical relic. But these electric cars that dominate the city streets, as soon as they get on the highway, facing long-duration cruising at speeds over 120 km/h, no matter how top of the line the model is, the power consumption will skyrocket like a dam opening its floodgates. The dashboard originally displayed a cruising range of 500 kilometers, often drops by 30% or even 40% at high speeds. The reason behind this is definitely not as simple as increased wind resistance. The real culprit giving global EV engineers a headache is actually hidden right inside the core component we explored in depth in our last video. It's the permanent magnet synchronous motor, abbreviated as PMSM. We know that permanent magnet motors can unleash extremely powerful torque at low speeds because their rotors are filled with NFEB magnets with extremely high magnetic energy product. This gives the rotor an inherently powerful magnetic field. When the stator coil generates a rotating field via 3-phase AC, the rotor's intense field will lock onto the stator field, achieving perfectly synchronized and efficient operation in stop-and-go city traffic. The conversion efficiency of this design is unbeatable, but physics laws like Faraday's law of induction and Lenz's law will not let anyone off the hook. The law tells us that when a magnet moves rapidly near a coil, a voltage is induced inside the coil, and the direction of this voltage is exactly opposite to the supply voltage that originally drives the motor. In engineering, we call this phenomenon Back-EMF. When you are speeding on the highway, the motor speed exceeds 10,000 revolutions per minute and even approaches 15,000 revolutions per minute. The powerful NFEB magnets in the rotor are frantically. At this point, the generated Back-EMF becomes massive, large enough to nearly offset the high voltage, as the effective voltage at the motor end decreases. This is why electric cars feel a sudden loss of acceleration power at high speeds, and the underlying physical limit for the spike in power consumption. To solve this inherent Achilles heel of EVs, for several decades, engineers worldwide invented an algorithm called field weakening control. Utilizing field-oriented control FOC theory, the input current is decomposed into Q-axis current responsible for torque and D-axis current responsible for the magnetic field. When Back-EMF is about to spiral out of control during cruising, the motor controller will forcefully inject a large negative D-axis current into the stator. It uses the electromagnetic field of the stator to offset and suppress the rotor's permanent magnetic field. By artificially weakening the total magnetic field strength, Back-EMF is reduced, allowing the motor to continue sprinting to higher speeds. This sounds like a very smart software solution, but it's actually a desperate and wasteful compromise. Because you have to know, those negative D-axis currents used to fight the rotor magnets will produce absolutely zero propulsion torque. It is purely fighting with the rotor's magnets. This means that on the highway, a large portion of the battery power is consumed for nothing in this unproductive magnetic confrontation. What's even worse, when these massive ineffective currents pass through the copper coils, they generate significant resistive heat, known as copper loss. This not only causes motor temperatures to skyrocket, greatly increasing the burden on the cooling system, but if deep field weakening continues under extreme heat, the strong reverse magnetic field from the stator could even potentially completely demagnetize the expensive magnets. Once irreversible demagnetization occurs, this motor is basically scrapped. So you see, you spend a lot of money on the world's strongest magnets, only to spend precious power to suppress them at high speeds. This is fundamentally a self-contradictory engineering tragedy. This is why the Porsche, taken to balance low speed starts and high-speed cruising, added weight and high mechanical complexity by installing a 2-speed gearbox on the rear axle. The goal is to lower motor speed via gear ratios To avoid the Back-EMF death trap, the BYD we discussed in the last episode chose another path, that is to remove the permanent magnets entirely and replace them with electromagnets, whose strength can be adjusted by current at any time. This fundamentally solves the high-speed field weakening issue, but the disadvantage of BYD is that the rotor generates heat, and the structure is exceptionally complex. Is there no perfect solution in this world that can preserve the permanent magnet motors, explosive low-speed power and low-temperature advantages, while being as effortless as an BYD at eliminating Back-EMF at high speeds? Yes, there is, and this seemingly impossible ultimate black tech is being quietly patented by the Chinese EV giant, BYD. They call this technology the Variable Flux Permanent Magnet Synchronous Motor. If you find this name too academic, the engineering circles in mainland China have given it a more grounded and vivid name: the mechanical gearbox inside the motor. This is an extremely crazy mechanical engineering miracle with a touch of brute force aesthetics. BYD engineers looked at the pain points of permanent magnet motors and came up with a bold idea. Since software field weakening is wasteful and generates heat, why don't we use pure mechanical physics to directly shut off the magnet's field? Of course, we can't actually dig the magnets out while the motor is running, so BYD utilized the fundamental logic of magnetic circuits to create a morphing motor rotor. To understand this black tech, you must first understand the characteristics of magnetic flux lines. Magnetic flux lines are like current. They are very lazy. They will always choose the path with the least resistance, which is the lowest magnetic reluctance. In traditional permanent magnet motors, the only way out for the rotor's magnetic flux lines is to cross the air gap between the rotor and stator into the stator to form a circuit. This is the source of the motor's torque, but in BYD's variable flux motor, the rotor's silicon steel sheet structure is no longer a solid piece of iron. Engineers carefully designed very complex slide cavities inside the rotor near the magnets and inserted sliding magnetically conductive iron blocks into these cavities. We call these magnetic short circuit blocks. This is a mind-numbing dynamic mechanical structure. When the car is driving at low speeds in the city, these blocks are held firmly in place by high-strength, precision reset springs. At this time, the magnetic circuit inside the rotor is disconnected. The flux lines cannot take shortcuts inside the rotor and must cross the air gap to project onto the stator. The motor then acts as a full-fledged, high-performance permanent magnet synchronous motor. It can explode with terrifying torque that shreds the asphalt instantly. But when you drive on the highway and pin the pedal down, the motor RPM begins to climb crazily, breaking 5,000, 8,000, and reaching 10,000 revolutions per minute. Is when the truly incredible physical transformation starts, deep inside the motor. As the speed gets higher and higher, the huge centrifugal force of the rotor begins to play its part. This centrifugal force is like an invisible giant hand, surging proportionally to the square of the speed. When the RPM reaches the critical point calculated by engineers, this massive centrifugal force finally defeats the preload tension of the springs. It flings the magnetic short circuit blocks outward, or in a specific direction, sliding them into a brand new position. This tiny mechanical displacement instantly opens a new magnetic flux highway inside the rotor. The flux lines that originally had to cross the air gap to the stator suddenly discover a low-resistance shortcut inside the rotor. So a massive amount of flux lines immediately turn back, passing through this slit-in magnetic block, forming a magnetic short circuit inside the rotor. It's like you've poked a big hole in a water pipe. The water pressure that was supposed to spray far away instantly leaks out through this hole. The result is that the effective magnetic field strength linking the rotor to the stator undergoes a physical collapse. Once the external field becomes weak, the Back-EMF that engineers loathe naturally drops significantly. What does this mean? This means the motor controller no longer needs to waste battery power on software field weakening to inject useless negative D-axis current to perform software field weakening. The motor instantly sheds its heavy electromagnetic drag. It can glide and cruise at ultra-high speeds with extremely low energy consumption, cutting the stator coils at high speed. This is exactly why it's called a mechanical gearbox inside the motor, because it completely eliminates the need for Porsche's heavy DC supplied by the battery pack and expensive external gearbox. Instead, it goes directly to the source of electromagnetism. It can no longer draw in current to generate torque, utilizing the rotor's own rotational kinetic energy to physically switch the motor's character. At low speeds, it's a beast with immense power. At high speeds, it instantly becomes a light and efficient long-distance runner. It sounds like the perfect ultimate solution, doesn't it? But if you're an engineer with a grasp of mechanical structures, hearing this must send chills down your spine. Because turning this perfect theory into a mass-produced part that can last 100,000 kilometers on the road is a hellish engineering disaster. First, let's look at the operating environment. This is a rotor spinning at 15,000 to 20,000 revolutions per minute. In such an extreme environment, even an imbalance of just a few grams will generate destructive vibrations, instantly tearing the motor bearings to pieces. And yet, inside this ultra-high-speed precision part, you are now inserting metal blocks that slide freely with RPM. For the motor's dynamic balance design, this is a complete and utter nightmare. Engineers must use the most advanced supercomputers to conduct infinite rounds of finite element analysis. They must ensure these sliding blocks, at any speed or temperature, maintain a perfectly symmetrical distribution of mass. Furthermore, the machining precision of these rails and blocks must reach a hair-raising micron level, which is 1,000th of a millimeter, the slightest tolerance or substandard surface roughness, under thousands of Gs of terrifying centrifugal force, would cause the blocks to instantly jam in the rails. If they jam and can't reset, your car loses its low-speed torque forever. This relies heavily on top-tier 5-axis CNC machines and near-zero fault automated precision assembly lines. Beyond that, there is an even more fatal problem: wear and fretting corrosion. As the vehicle accelerates and decelerates, the motor speed is constantly changing. This means the sliding blocks and springs are subjected to countless instances of tugging and friction between force and inertia. And usually the inside of a motor rotor is a closed, high-temperature environment. How do you ensure these mechanical structures, after hundreds of thousands of operations, won't suffer metal fatigue and snap the springs? Or that the sliding blocks won't wear down and produce metal debris due to dry friction? Once metal debris falls into the air gap between stator and rotor less than 1 millimeter, the entire motor will instantly be destroyed. To solve this severe lubrication and cooling issue, engineers will likely introduce the dynamic oil cooling technology for hollow shafts that we mentioned in the ESM video. This involves using a bored-out motor spindle to take cooling oil with insulating and lubricating properties, and under the influence of high-pressure centrifugal force, spray it directly into the rotor's internal cavities. This cooling oil not only carries away heat from the magnets and silicon steel, but more importantly, it provides a life-extending lubricating film. For these precision sliding mechanical structures, it prevents direct metal-on-metal friction and significantly extends the lifespan of this morphing mechanism. With the hardware nightmare addressed, the software engineers are about to have a breakdown as well. In traditional motors, electromagnetic parameters like flux linkage and D-axis Q-axis inductance values are basically fixed constants at specific temperatures and currents. The FOC algorithm inside the motor controller only needs to build a set of mathematical models to precisely control the current. But in a variable flux motor, at the moment the mechanical displacement occurs in the rotor, the physical characteristics of the entire motor change completely. Reluctance, inductance, and flux linkage all change. This is equivalent to the motor instantly mutating from motor A into motor B while running at high speed. If the motor controller specifically the microprocessor in the inverter, isn't powerful enough, or if the algorithm isn't smart enough to detect this physical mutation within a microsecond time frame and switch to the corresponding control matrix, the motor will immediately lose sync due to current loss of control. At best, the vehicle will experience severe jerking. At best, the vehicle will experience severe jerking. At worst, it could directly fry the IGBT or SiC power modules. Therefore, this motor must be paired with extremely advanced sensorless observer algorithms. It uses ultra-high-frequency current sampling, much like an EKG, to monitor minute internal electromagnetic characteristic changes in real time. It might even need to combine neural networks or AI predictive models to switch control parameters seamlessly the moment the mechanical structure begins to shift. This ensures that while the driver is pressing the accelerator, they won't feel a thing regarding the violent physical deformation occurring inside the motor. This is the perfect fusion of hardware brute force aesthetics and ultimate software control. In summary, from traditional induction and permanent magnet motors to the ESM we discussed last time, and now to BYD's variable flux permanent magnet synchronous motor, we see how human engineers use every means possible to fight the laws of physics and squeeze out every drop of potential efficiency. BYD's technical route chooses the toughest challenge in mechanical precision manufacturing to trade for a vast new horizon in electromagnetic control. It doesn't just completely shatter the curse of electric vehicles becoming power-hungry beasts on the highway. It demonstrates that in an era where basic physics is locked, material science, CNC, precision machining, and advanced software algorithms are the only paths to breaking the technological ceiling. In the world of engineering design, there are never perfect solutions, only the optimal ones refined after constant attempts and compromises at the limits. If you are interested in this crazy design of physical deformation for magnetic flux, or the sensorless observer algorithms mentioned, feel free to leave a comment below to let me know. Your every discussion is the motivation that drives us to dismantle deeper engineering principles, dismantling the world's operation through an engineering lens. If this purely hardcore script gave you a new perception of motor technology, don't forget to subscribe and like. See you next time.